In the previous lecture, we have talked about the uniform convergence of function. So when we can say that this series is uniformly convergent if the partial sum of that, that is we have denoted as Sn, which is the sum of first n terms. If this partial sum is converged to some function uniformly as n tends to infinity, then we can say that this series is converged to F uniformly. To check whether the given series of function is uniformly convergent, we have learned one result is called the Weierstrass M test. So what is the Weierstrass M test? If each of this Fn are bounded by some constant sequence for every x is in E and n in N, and the summation of Mn is convergent, then summation of Fn is uniformly convergent. So this was known as Weierstrass M test. In the previous lecture, we have discussed the proof of this theorem. Here, our objective is to solve certain examples of uniformly convergence using this M test or any other method which come across. So ultimately, the objective is to whether the given series is uniformly convergent or not. That we will discuss. So let us have first example. Prove that the series summation k running from 1 to infinity 1 upon k power p cos kx, where p is greater than 1, converges uniformly. So this is the problem, that this series is converged uniformly. So as per this, you have to find out this is what is your here. Fn x is actually 1 over n power p cos nx is there. This is your Fn. Here index is k, so if you want that you can write fk, then also it's fine. For every x, it is an R, because there is no domain or what, there will be no value of x is given. So this function is valid for any value of R. X belongs to R, and your value of p is greater than 1. This is given. And for every n, it is in N. This is true. Now we have to find out, as per the Weierstrass M test, some constant sequence. So this sequence of functions, that is 1 upon n power p cos np, cos nx, will be bounded by some constant sequence. And that can be easily seen that if I can have mode of Fn of x, which I can write down less than or equal to mode of cos nx upon n power p. And we know that cos is always less than or equal to 1. So that's why this is less than or equal to 1 upon n power p. For any x belongs to R, we can write this. Now one should note that this 1 upon n power p by p test, summation 1 upon n power p is convergent. Convergent using p test. P test says that if you have forgotten what is the p test, that is p test says that summation n raised to p is convergent if p is greater than 1, and it is divergent if p is less than or equal to 1. This is known as a p test. So using p test, this summation of 1 upon n raised to p is convergent, because here the value of p is greater than 1 is given to you. So hence by Versta's M test, we can say that summation cos nx upon n power p is uniformly convergent. This is the example that we have done. Let's take another example. Take another one. Prove that for every x in closed interval -1 to 1, the series 1 plus x square by 2 factorial up to so on x power n upon n factorial so on is uniformly convergent. And probably you know that this is very well known series. It's a series of e power x. Here for every x is in this interval, we have to prove that this is convergent. So if you can write the solution for this, here your fn of x is x power n upon n factorial. This is your fn of x. And given that x is between -1 and 1, for any x belongs to -1 and 1, we can write x power n factorial upon, x power n upon n factorial is less than or equal to 1 upon n factorial. We can write, because mode of x power n, as your x is less than -1 to 1 or in between -1 to 1, this value is always there. Now ultimately you have to prove that this n factorial is convergent. Summation of, this is a constant sequence. So if you want to apply the Versta's M test, you have to prove that the summation of 1 upon n factorial is convergent. So now what we note, either you can use the ratio test, root test, whatever the test, or a comparison test, whatever you like, you can apply for this summation of 1 upon n square. There are many ways to prove that summation of 1 upon n factorial is convergent. So one of the ways is this. We know that 1 into 2 is greater than 2. 1 into 2 into 3 will be greater than 2 into 2. 1 into 2 into 3 into 4 will be greater than 2 into 2 into 2. And if you go further in the same manner, I can say 1 into 2 into 3 into 4 up to n. This is greater than or equal. Afterwards, all of them are greater than. Is greater than 2 into 2 into 2 up to n minus 1 times. So finally what we got, it's n factorial is greater than or equal to 2 power n minus 1 for every n it is in this. And therefore 1 upon n factorial is less than or equal to 1 upon 2 power n minus 1. For every n, it is in n, this is true. Now by comparison test, on this side, this is a geometric series with ratio 1 by 2. So here, summation of 1 upon 2 power n minus 1 is a geometric series with r is equal to 1 by 2, which is less than 1. Therefore, summation of 1 upon 2 power n minus 1 is convergent. Therefore, by comparison test, since the bigger one is convergent, its smaller one is also convergent. Summation of 1 upon n factorial is convergent. Since this summation of 1 upon n factorial is convergent by Weierstrass and test, the series summation of x raised to n upon n factorial is uniformly convergent. So let's complete the solution for this example. Let's have the next example. If the given that if summation of an is absolutely convergent, we know that absolutely convergent means summation of mode of an is convergent. Then prove that summation of an x power n upon 1 plus x power 2n converges uniformly for every x belongs to R. So for any x, we have to prove that this series is uniformly convergent. So ultimately the idea is you have to looking at this Fn. And in this Fn here, Fn of x is an x power n upon 1 plus x power 2n. This is your Fn. So the idea is to find out the maximum value of this. That means I need to find out some constant sequence, which is for that this is bounded. So ultimately it is better to find out what is the maximum value or supremum value of this function, that is x power n 1 plus x power 2n. This is the idea. So if I can find out whatever the maximum value or supremum value of this x power n upon 1 plus x power 2n for any x belongs to R, we can get the maximum value. If this function is bounded, then we are through. So for that, I may take or assume that g of x will be x power n upon 1 plus x power 2n for any x belongs to R. So ultimately, I want to find out what is the supremum value of this function gx. And we know that how to calculate the supremum. To calculate the supremum, we can just find out first of all its derivative g dash of x. A g dash of x. So by division rule, we can say that this is 1 plus x power 2n square, 1 plus x power 2n as it is. The derivative of x power n, that is n into x power n minus 1 minus x power n as it is, the derivative of 1 plus x power 2n, that is 2n into x power 2n minus 1. And if you simplify, then this will gives you n into x power n minus 1 plus n into x power 3n minus 1 minus 2n into x power 3n minus 1 upon 1 plus x power 2n square. And then further you simplify, this is n into x power n minus 1 plus, minus n into x power 3n minus 1 upon 1 plus x power 2n square. Now, to find out the stationary value, let's take this g dash of x is equal to 0. This will implies the numerator will be 0, so it is n is common. If I take common out x, n into x power n minus 1, if I take common, then here it is 1 minus x power 2n left. that is equal to 0. So this will gives you n will never be 0. So it will gives you x is 0 or x power 2n is 0. So x power 2n is equal to 1. So this will gives you x is 0 or x will be 1 or it will be minus 1 because it is x square power n. So it may gives you a value x is 0 or x is 1 or x is equal to minus 1. All other values of this will be complex numbers. So we are not talking into that. Now to calculate the whether this x is equal to 0, 1 and minus 1 are maxima of the function g, you have to see what is g double dash of x. So to calculate the g double dash, we have to find out what is the derivative of this function. This is g dash of x. So let us calculate the derivative of this again by division rule. This is 1 plus x power 2n whole raised to 4. 1 plus x power 2n whole square as it is. Now the derivative of this numerator, that is n into n minus 1, x power n minus 2, minus n into 3n minus 1, x power 3n minus 2, plus, sorry, minus this quantity as it is. That is exactly the same quantity we have here. That is n x power n minus 1, 1 minus x power 2n. This is there. And the derivative of the denominator, that is 2 times, because the derivative of this quantity is 2 times 1 plus x power 2n into 2n into x power 2n minus 1. So this is the derivative of this g double x or g of x. Now we have to calculate this g double dash at this point 0. If you substitute 0 here, this term will be 0, that you can see. And this is x into anything, so this will be 0. So that is nothing can say about x is equal to whether it is maxima or minima. G double dash at 1, let us see what is g double dash at 1. Now g double dash at 1, this value will be tends to 0 because it is 1 minus x power 2n is there. So this will be 0, this term is 0. Here the term is left, which I can say it is 1 plus 1 powers this n into n minus 1 into 1 minus n into 3n minus 1 into 1 upon 1 plus 1 raised to 4, that is 2 raised to 4. And if you further simplify this, this is cancel out, this will be 2, so it is 1 upon 4 n square minus n, this is minus 3n square plus n. This will cancel out. So finally this will gives you answer minus 2n square upon 4, so that is minus n square by 2. Which is less than 0, which is negative. Hence we can say that x is equal to 1 is the maxima of function g. The same behavior can be done for minus 1, but we are not interested for that also, because I want at least one value on which the function g is maximum. So this g function has a maximum value if x is 1. So therefore g of 1, so hence what we can say, therefore, so now mode of fn of x, which we have, it is mode of an x power n upon 1 plus x power 2n will be less than or equal to an into g of 1, because mod of an into g of 1, because the maximum value of this x power n upon 1 plus x power 2n will be g of 1, mod of g of 1. So this is mod of g of 1 that we can calculate, that is mod of an into mod of 1 upon 1 plus 1. So therefore this is mod of an upon 2. So hence what we can got, therefore mod of fn of x is less than or equal to mod of an upon 2 for every n. This is there. And we have given in the hypothesis that summation of an is absolutely convergent. That means summation of mod an is convergent, which is already there. So what we can say is the summation of an x raised to n upon 1 plus x raised to 2n. So therefore since summation of mod an is convergent, this is by hypothesis, by Vasta's M test, summation of an x raised to n upon 1 plus x power 2n is uniformly convergent. And this completes the proof, or this completes the solution for that example. Let's have one more example. So that the series summation k running from 1 to infinity x e power minus x power k is uniformly convergent in closed interval 0 to. So here the function is given as x into e power minus x power k, and your value of x is between this 0 and 2. So solution, to find out the solution, here fn of x is x e power minus x power m. For every x it is in closed interval 0 to, and for every m. So you can just see that if I can find out this value, that is x upon e power x will be less than or equal to some quantity, then we are through. So for that I may take that g of x is a function which is x into e power x. For every x it is in closed interval 0. Now we need to calculate what is the maximum value of this g function. That is, for that consider g dash of x is equal to 0, which implies the derivative of this x e power minus x into minus 1 plus, using the product rule, e power minus x as it is, derivative of x is 1 equal to 0. E power minus x is common out. So this will give you minus x plus 1 equal to 0. So this will give you x is equal to 1, because e power x will never be 0. So this will give you x is equal to 1. Now to check whether this x is equal to 1 gives the maximum value or not, we have to see what is g double dash of x. G dash is this. So to calculate g double dash, we can have the derivative of this, that is e power minus x as it is, the derivative of x minus 1, this is minus 1, plus minus x plus 1 as it is, derivative of e power x is e power minus x into minus 1. You just see that minus sign is common out, and inside minus e power minus x is common out. Here a left is 1 minus x plus 1. Now g double dash at 1, that is minus e power minus 1 into 2 minus 1, because 1 plus 1 is 2 minus x is 1, and this will gives you negative. So therefore x is equal to 1 is a maxima of function g. Hence mod of g of x is less than or equal to g of 1. But g of 1, we can say it is 1 into e power minus 1. That is 1 upon e. Now, what is your mode of fn of x? Will be less than or equal to fn of x, we know it is x into e power minus x raised to n. So according to this will be less than or equal to e power 1 upon e power 1 upon e power n. And we know that this summation of 1 upon e power n is convergent due to the geometric series with the ratio is less than 1. So we note that summation 1 upon e power n is convergent by geometric series test, as your r, which is 1 upon e, which is less than 1, because the value of e is 2.7, 1 upon 2.7 is always less than 1. So hence by Vasta's M test, the summation x into e power minus x power k is uniformly convergent. So in that manner, you can solve many examples based on this uniform convergence of a series. There is one more test is there, but we will not discuss the neither example or the proof of this theorem or this test, I can say. So whenever this Vasta's test is failed, that means you cannot able to find out some constant sequence which bounded by some function, which bounded to this sequence of function. Then you can able to apply this Dedekind test. I'm not discussing the any of this example of this Dedekind test, neither and proof of this Dedekind test. But for your knowledge, I'm just sharing this Dedekind test to you. And this is very well-known topic for the JAM examination, also in the NET examination. So this Dedekind test tells you this: the series summation of a n tends to infinity a n of x, which is a function of sequence of function, a n of x is a sequence of function into d n of x, converges uniformly on E if the first one, the Sn of x is equal to summation kn running from n, that is the partial sum of this an, ak of x, is uniformly convergent, uniformly bounded on it. What do you mean by uniformly bounded? That means there exists a constant k greater than 0 such that mod of Sn of x is less than or equal to k for every n and for every x. It is in E. This is known as uniformly bound. That means this an is partial sum of this an. sequence of series of an is uniformly bounded. It is a bounded sequence. The second one is this, that is n running from 0 to infinity.
Sir,
Bn, yes.
we have Savan sir's lecture now, sir.
Yeah, I'm just finishing after this statement. Is uniformly convergent on E. So if this series is uniformly convergent, and the third things you need to check is the Bn of x is tending to 0 as n tends to infinity uniformly on E. Then this series summation of an into bn is uniformly convergent. This is known as a Dedekind test. We are not going to discuss any proof of this or neither an example of that. In some of the reference book, you have already solved some of the example is there to how to apply this test. So you can go through it. You can try to find out how to apply this theorem. This is very important topic for the NET examination. So I just suggest that you can go through this Verstas test, examples on Verstas test, also the examples on Dedekind test. Okay. So that's it for this. You have any questions, you can ask.